What is vapor pressure? If you take a liquid in a container and you allow it to start evaporating, the space above the surface of the liquid will start getting gas molecules. Now, if you put a lid on the container, then the gas molecules are trapped. Gases impart pressures, so as that builds up, gas molecule goes back into the liquid phase. As this happens, you finally reach a state at which the exiting evaporation rate equals the entering condensation rate, and you reach what is called equilibrium. So when those two rates are equal, you establish a constant pressure inside your container. That pressure is called the vapor pressure of that liquid. At boiling point, vapor pressure is equal to the pressure exerted on the vapor, which is the external pressure usually taken as 1 atm at boiling point.
Vapor pressure versus temperature data is a prerequisite for several engineering and scientific processes. Just some of the applications for vapor pressure versus temperature data run from high penetration welding, additive manufacturing, and the design of nuclear reactors. Keyhole mode welding requires vapor pressure versus temperature data to explain the formation of a depression on the surface of the melt pool. Additive manufacturing, and welding to a lesser extent, relies on vapor pressure data to power understandings of how the loss of alloying elements from the melt. Pressurized nuclear reactors, regardless if using water or another coolant, use vapor pressure versus temperature data to drive turbines to generate electric power.
Even though the vapor pressure data is important for so many applications, the work on the vapor pressure of elements hasn't advanced much since the 1980s when researchers compiled the vapor pressure of several elements. This vapor pressure data at various temperatures was then fitted using linear regression to provide relations between vapor pressure and temperature. However, for most of the elements, the resulting fitted equations are only valid for a narrow temperature range, much below the boiling point of the element. Another issue is that these sources provide multiple equations to represent the changes in vapor pressure, and for some elements, the temperature, which corresponds to 1 atmospheric pressure, does not match the boiling point of the element.
In this research, for the first time, we have used a genetic algorithm to derive vapor pressure versus temperature relations. We took literature data at low temperatures. At high temperatures beyond the boiling point, we used data obtained from the Clausius Clapeyron equation. Then we use a genetic algorithm to fit these data, as you can see here. This fitting is nonlinear as shown here. The fitted equation has inverse relation, logarithmic relation, and so on and so forth between the vapor pressure and temperature. Here, the genetic algorithm optimizes the four constants A, B, C, and D for different elements. Uniquely, we get vapor pressure and temperature relations for a broad range of temperatures that was not there before. But why we use genetic algorithm? This is because genetic algorithm is a robust optimization algorithm, especially for complex, nonlinear, or discontinuous functions. Secondly, it is designed to search for global optima rather than the local optima to find potentially the best solution. And finally, genetic algorithm provides multiple simultaneous solutions which can be useful for problems where there might be many optimal solutions. Here, we used differential evolution type genetic algorithm because it's robust, especially in fitting complex and nonlinear functions. If you are interested in knowing more about differential evolution type genetic algorithm, Please follow this paper as shown here.
Understand the approach of this work using the example of silicon. For this, we use experimental data as well as data synthesized using the thermodynamic Clausius Clapeyron equation. Here, the black triangles represents the experimental vapor pressure data taken from handbook. As seen, this experimental data is available for a temperature range of 1700 K and 3400 K. The vapor pressure at 1700 K is 10 to the power minus 8 atmosphere, and that at 3400 K is 0.5 atmosphere. Vapor pressure data above this temperature is synthesized using the Clausius Clapeyron equation and is represented by the red circles in the figure. In the Clausius Clapeyron equation, using the information of pressure P1 at temperature T1, the pressure P2 at any other temperature T2 can be calculated. Using the normal boiling point of silicon as T1 and its corresponding pressure of 1 atmosphere as P1, the vapor pressure at temperatures greater than the boiling point are calculated. The first red circle represents the boiling point of silicon and the last red circle corresponds to a vapor pressure of 10 atmosphere. This combined experimental and synthesized vapor pressure temperature data is then used in a genetic algorithm to provide the coefficients A, B, C, D of this equation number 2. This equation is represented by the blue line in the figure and is able to represent the vapor pressure of silicon from 10 to the power minus 8 atmosphere to 10 atmosphere. This relationship also correctly predicts the boiling point of silicon and has a low RMSE error of 0.064. The RMSE error is calculated based on the difference between the vapor pressure temperature relation using the optimized coefficients of genetic algorithm and that of the data that was used as an input to the genetic algorithm model. Same approach, we calculated the coefficients of the vapor pressure temperature equation for 50 elements which are marked in green. These coefficients are able to represent the vapor pressure from 10 to the power minus 8 atmosphere to 10 atmosphere for each of these elements. This vapor pressure temperature relationship also correctly predicts the boiling point of the respective element and has a low RMSE error.